Hey guys, and welcome to a quick explainer video where we're going to talk about hybridization on a conceptual level. So in this video, we're not going to be looking at orbitals, or at least not what they actually look like, but we're going to be drawing a parallel with these virtual pieces of paper that I have drawn. So I have a blue piece of paper and 3 pink pieces of paper. And the blue represents the s orbital and the pink represents the p orbitals. All right, because hybridization is this concept that we use to explain how do we get from s orbitals and p orbitals, which have very distinct shapes, all right, to the geometries that we see in molecules like trigonal planar or tetrahedral. All right, so what we say is that these orbitals, these s and p orbitals, do something called hybridize. And so we say that these discrete orbitals combine. All right, and we'll talk about what we mean by combine. We say that they combine and create hybrid orbitals, which can then exhibit the geometries that we observe in nature. So let's look at this with our example with these pieces of paper. So in most organic chemistry textbooks, they say that you combine these orbitals, but that's a very weird way, I feel, of describing it. Because when we think of combine, when we say that we add the orbitals, we think that the two things become one thing, but that's not how it works. So let's take a look at one of our hybrid orbitals that we can have, which is an sp hybridized orbital. All right, so there we go, sp. So in an sp hybridized orbital, all right, the way that the naming mechanism works is that the orbitals are listed. So this is S1 and P1. So we took one s orbital and we took one p orbital. All right, and we're mixing them together, right? But in this analogy, we're using pieces of paper. So it's very hard to take a piece of paper and mix them up. So what we're going to say for this example is we are going to cut the pieces of paper in half and add them together, right? So now we can see, okay, I have a piece of paper that's SP. It's half S and half P, but I end up with 2 pieces of paper, because if I cut 2 pieces of paper in half and switch the halves and recombine them, I still have 2 pieces of paper. Orbitals work exactly the same way. We have to conserve the number of orbitals that we have. Just like in general chemistry, when you took 2 hydrogen atoms and you overlapped their s orbitals, you ended up with a bonding and an anti-bonding. Why did you have 2? Because you started with 2. You started with 2 1s orbitals, and so you needed to have 2 orbitals in the end, a bonding and an anti-bonding. Whenever you combine orbitals, it's the same way. So if I'm combining 2 orbitals, I have to end up with 2 orbitals. And so we say that these are sp. So with pieces of paper, right, they don't blend homogeneously, but in the real world, right, these orbitals are not just cut out like half a sphere connected to half a dumbbell. All right, they homogenize for the real orbitals, but for our piece of paper analogy, all right, this is what we're going to work with. And we can see here our 2 p orbitals that weren't involved in this hybridization process. They're still there. So how does this connect to Vesper theory? Well, our electron groups, right, which Vesper theory says if you have 2 electron groups, it's linear, 3 electron groups, trigonal planar. When we use hybridization, only orbitals that have s character, they have a little bit of s in it, those are the only ones that count. So if we look at our 4 orbitals, all right, how many have s character? 2. So we have 2 electron groups, which means it's linear. So what do I mean by it's linear? Well, we use this term sp or sp2 or sp3 to describe a couple of things. We can say that this orbital is sp hybridized, or if we're talking about an atom, we can say that the atom is sp hybridized. So if I draw acetylene here, this carbon, if we were just using Vesper, right? We have 2 electron groups on either side. The carbon is bonded to a carbon and it's bonded to a hydrogen. Therefore, 2 electron groups. There are 2 packets of electrons on either side, or 1 on each side. Therefore, it's linear. So atoms that are linear are always sp hybridized every single time. And when it's linear, right, if it's sp hybridized, it will always have these same 4 orbitals. Any atom that's sp hybridized has 2 sp orbitals and 2 p orbitals every single time. It doesn't matter what atom on the periodic table it is. Carbon, nitrogen, oxygen. If it's sp hybridized, it has 2 orbitals that are sp hybridized and 2 orbitals that are unhybridized, 2 unhybridized p orbitals every single time. Let's look at our next one. Let's look at sp2. All right, where from the name, all right, we can see, okay, we're going to use 2 p orbitals for sp2. And again, if you want, you can put a 1 after the s to remind you that there's 1 s and 2 p orbitals. So we combine 3 total orbitals, which means that we're going to have 3 hybridized orbitals. All right. So we'll get 3 orbitals that are sp2 hybridized. So what does that mean? Well, it means that they're 1/3 s and 2/3 p. What happened to that other 4th orbital? It's still there. We didn't touch it, but it's still there. So again, with Vesper theory, only atoms that have some bit of s character count for our electron groups. So we have 3 orbitals that have some sort of s character. They have some blue in them. So 3 electron groups, that is trigonal planar. Any atom that's trigonal planar is sp2 hybridized. Any atom that's sp2 hybridized has these 4 orbitals. It has 3 sp2 orbitals and 1 unhybridized p orbital every single time. It doesn't matter what the atom is. All right, and let's look at our last one, sp3. So when something is sp3 hybridized, right, that means we have an s orbital and 3 p orbitals that hybridize together. So this means that for this hybridization, we're using all 4 of our orbitals available to us. Okay, so if these guys hybridize, we have something that looks like this, where now we're going to have 4 sp3 orbitals at the very end. Each one will have 1/4 of the s and 3/4 of the p. Because again, we're thinking of this in terms of cutting a piece of paper, right? If we wanted to hybridize all of these pieces of paper together, this is what they would look like. So now we have 4 orbitals that have some bit of s character in them. So that's 4 electron groups. So atoms that are sp3 hybridized have a tetrahedral geometry. Any atom that is tetrahedral is sp3 hybridized, and it has 4 equivalent sp3 orbitals. So in this video, we're not going to look at what these orbitals look at. We're going to do that, at least if you're a student in my class, we're going to look at that in our lecture. It's also in your textbook. But if you're not a student in my class and you happen to find this video, I'm sure that you'll talk about it in your course. But I wanted to just make this video to demonstrate what hybridization looks like before you start looking at orbitals and energy diagrams of all the different relative levels of energy associated with each orbital. This is just a video trying to convey, what do we mean by hybridization? What is this phenomenon? Again, it's our explanation of how we take s orbitals and p orbitals, which cannot form linear geometries or tetrahedral or trigonal planar geometries, and how we get to what we observe.